Welcome, dear students. So in the last lecture, we have studied the mathematical basis of finite element. We have seen what is the need of understanding the mathematical basis, and we have seen the two approximate methods, namely Galerkin's method and Rayleigh-Ridge method, to solve boundary value or initial value problems. And we have also studied the details of Galerkin's method, how the weak formulation is done, how the differential or partial differential equation is converted into integral equation, and then we have also studied the physical interpretation of Galerkin's weighted residual method, where we found that Galerkin's weighted residual method can also be interpreted as another statement of virtual work principle, where the weight functions applied to the residual can be visualized as some virtual displacements. And we saw that the work done by the internal forces over the virtual displacement is equal to the work done by the external forces over those virtual displacements. Now today we will see some example application of this Galerkin's method, weighted residual method. We'll take up our familiar problem of axial deformation of a prismatic bar, homogeneous prismatic bar, and we'll see how we can apply this classical Galerkin's method. And then we will also highlight what are the problems or disadvantages of this classical Galerkin method, and then we will see that those disadvantages are the motivation of casting this Galerkin's method into the finite element form. And finally, we will derive the finite element equations for a bar element, two-noded bar element, using Galerkin's weighted residual method. So let's start. So let us take up this prismatic axially loaded bar. It has a constant cross section of A, and it is a homogeneous bar with an Young's modulus of E. It has a load at the end, which is a tensile or positive load at the end. Its value is P, and the length of the bar is L, and at the left end the bar is fixed, so that the deformation at this point is 0. Okay. So now if I write the weak form of this problem, what shall we find? We have already studied the weak form equation. This was my equation in weak form. Okay. And here, of course, in our problem, this term will not be there, because at the left end there is one essential boundary condition, which is the deformation is 0. Here force boundary condition is shown, natural boundary condition is shown, but in our problem we have an essential boundary condition. So accordingly we can write the weak form of this problem like this. You remember, I think we have at the right end we have P and when I multiply it by weight function wi at L minus integration of 0 to L ddx of AE du tilde dx plus I also have a linearly varying surface traction, so Bx, this whole thing when I multiply by the weight function Wix dx must be 0. So this is my weak form. All right. Okay, let me write this in an appropriate place. Okay. So this is my weak form. And what is my essential boundary condition? Essential boundary condition is that EBC is u at u tilde at 0 is equal to 0. When x is 0, the deformation is 0 because it is a fixed end. Now in this method, you remember that we assume some approximate solution, which is my u tilde. So as a starting point, let us assume a linear polynomial. Okay, so linear polynomial. Or the solution is linear solution. Okay, so let us assume that u tilde is, say, a naught plus a1x. Okay, and by applying this essential boundary condition, what we get at x equal to 0, u tilde is 0, therefore I get 0 equal to a naught plus 0. Hence I know that u tilde becomes simply a1 into x. Now my job is to find out the value of a1. Okay, and therefore what is my du tilde dx? Because I need to find out this term because I have it in the weak form. So let us find out du tilde dx, and we know that it is nothing but a1, right? And now I can write these values in the weak form. Okay, so substituting into weak form, what I'll get P into Wi at L minus integration 0 to L ddx of AE into du tilde dx is a1, so I'll write a1 into this wix, okay, into wix dx. I have separated the integral terms, okay, plus 0 to L, integration of 0 to L bx into wix dx. This must be 0. Now you remember that in Galerkin's weighted residual method, my weight function are the partial derivative of the approximate solution. Okay, weight functions are the partial derivative of the approximate solution, and therefore now I have what is my approximate solution? My approximate solution is this, right? Let me show you. My approximate solution is this, and therefore what is my partial derivative? Partial derivative will be, let me go to the next page. Oh, sorry. So my partial derivative will be, or the weight functions will be, wi is my del u tilde del ai, right? Del ai, and therefore my w1 here, because I have only one term in the u tilde, so w1 will be my partial derivative of okay, let me write it down, del a1 of u tilde is a1 x, and this is nothing but my x, right? Del a1 of a1x is x, and therefore now what is my w1 at L? So w1 at L is L, is not it? And therefore similarly w1 at 0 is obviously 0. Now these terms will be needed in while doing this integration by part. That's why we have found these values now. Now if I substitute these values, in the weak form here, what I will get? I'll get so substituting the above in equation 1c, let me call this as equation 1. I am getting P into W1L. W1L is L, so PL minus integration of 0 to L AE times A1 into WI, and W1 here is X only, therefore W1 W1 is my x, and therefore A1 into um, so now when I substitute these values here, and when I apply the integration by parts rule, you know that the order of differentiation will now move to this function. Therefore, I will have AE into A1 into dW1 dx into dx, right? I'll get this term from the above, plus the other term will be integration of bx into w1 x dx. Okay. So now, since w1 is x, dw1 dwx is 1, is not it? And therefore I can write this as p into L minus this AE is a constant, so I will take it outside because it no more depends on L. So 0 to L A1 into 1 dw, let me write it here, w1 is x, so also dw1 dx is my 1, so a1 into 1 into dx plus integration of 0 to L bx into w1 x. w1 is x, so I have another x here into dx, and this is of course 0. Okay. So now we can simply integrate it, pretty easy. So therefore PL minus AE into, this is my x, so AE into A1 into integration of 0 to L dx is L plus bx square dx is, b is a constant, so b x cubed by 3, so L cubed by 3 is 0. So from here I can find out what is value of A1. Okay, therefore A1 will be equal to 1 upon AE L into PL plus BL cubed by 3, or this is nothing but P plus BL square by thrice AE. This is the value of A1 we have got, right? No, I must have a 3 here because I have added these two fractions. All right, and once I get this A1, therefore my U tilde or approximate solution is a1x. So thrice p plus bl square by 3ae into x. So this is the approximate solution we have arrived at. All right. So this is my solution. I'm sorry. So this is my answer. Now let us see whether this solution fulfills the natural boundary conditions or not. For that, what I will do, I know that at x equal to L, my load is P, and the load can be obtained, you remember, in terms of natural boundary condition. Let us check the natural boundary condition, fulfillment of natural boundary condition. So we know now that P at x equal to L is what? AE, A into stress is E into strain, so E into strain is du tilde dx at x equal to L. Right? Now what is here du tilde dx? From here, from the solution, from the linear solution, du tilde dx at x equal to L is just this factor, right? So it is thrice p plus bl square by thrice ae, right? Therefore NBC at x equal to L is AE times this value. So when I multiply this by AE, I'll get 3p plus BL square by 3, that is my P plus BL square by 3. Which is not equal to P. So we have seen that this linear weak solution does not fulfill my force boundary condition or natural boundary condition at x equal to L. So this is the disadvantage of this solution, right? So if I now use a higher order solution, then maybe this error will reduce, and if I take a cubic polynomial, then of course we will get the correct result, because how do we know that? We know that by the fact that the actual solution, exact solution of this problem was a cubic equation in terms of x. I hope you remember. Let me show you this. So we, by exact analysis, the true solution, by integrating the actual differential equation, we had got this as the true solution, which is a cubic polynomial, right? This is a cubic polynomial in X. So if I assume a cubic polynomial, obviously we will have the solution which will fulfill the natural boundary condition at x equal to L. Okay. And in between I can have a quadratic solution. I can assume a quadratic polynomial for the approximate solution, and I leave it to you as a practice problem. Okay. So you please try to find out what is the solution for, what will be the solution for a quadratic equation, and I will solve it for your benefit, assuming a cubic solution, just to see that it fulfills the actual boundary conditions. Okay, so let us now try cubic solution. So let us assume a cubic polynomial. So let u tilde be a0 plus a1x. Remember, we must take a complete polynomial. So a2x square plus a3 x cube. Okay. And when my essential boundary condition is fulfilled, so my ABC is u tilde at 0 is 0, and therefore my a0 will be 0, just like the earlier case, and hence my u tilde is a1x plus a2x square plus a3x cube. So this is my admissible solution now. Okay. So this is my admissible solution because it fulfills the essential boundary condition. All right. Now therefore let us find out du tilde dx, because this term is necessary in my weak form. So du tilde dx is a1 plus twice a2x plus thrice a3 x square, right? And let us find out the weight functions. So w1x is my del u tilde del a1, and del u tilde del a1 is x square del u tilde del a1 is what? x, right? It is x. Remember, it is partial differentiation, so these terms will not come into picture. So W1 is x. Similarly, W2 x is my del u tilde del A2, and that will be my x square. Am I right? And also W3 x is similarly thrice x square, right? Sorry, x cube. I'll look into this one. So del u tilde is this, so the partial differential of this with respect to A3 is x cube. Now we will write down the values of these weight functions at x equal to 0 and x equal to L. So W1 at 0 is 0 and W1 at L is L. Similarly, W2 at 0 is 0 and W2 at L is my L square, and W3 at 0 is 0 and W3 at x equal to L is L cube. Now we will use all these terms in the weak form. Okay, so let us substitute all these in the weak form. So what was my weak form for our problem? Weak form is P into L minus 0 to L. AE I will take outside. du dx. So du dx is this one, a1 plus twice a2x plus thrice a3x square. So a1 plus twice a2x plus thrice a3x square into dw1 dx, right? So dw1 dx from here will be 1 once again, so I'll put 1 into dx, right? Into dx plus 0 to L b x square dx. B is a constant, so b x square dx. And and this is 0, of course. So from here PL minus AE into, integration is pretty easy, so a1 dx is a1x, so a1 into L it will be plus twice a2 into x square by 2, so L square by 2 plus thrice a3 into a cube by 3 x cube by 3, so l cube by 3. So this is my first integration, plus b l cube by 3 is my 0, right? So this is one equation which contains a1, a2 and a3. Okay, so let me number it as equation say small 1, Roman 1. Okay, and similarly, if I use the second if I use the second weight function, then what I'll get so in the similar manner, we are writing the weak form for the second weight function here, p into second weight function at x equal to L minus AE du tilde dx into dw2 dx and dx integration, and the other term is bx into d2 w2x dx. Now we have already got the value of w2x is x square, so dw2 dx is twice x. Similarly, we can write w3 is x cubed, so dw3 dx is thrice x square. That will be needed in the next equation. And w2l is l square, so I can write here as this as l square p into l square minus AE into dw2 dx. dw2 dx was twice x, so this is my twice x dx, and w2x is x square, so this is my value x square. Now I need to find out the integral, and if you find out the integral, then I'm just, because it is quite easy integral, I'm just writing the final result. So PL square minus AE into what I can write is A1 L square after simplification, okay, plus 4A2L cube 4A2 L cube by 3 plus 6A3 L to the power 4 by 4 after putting the limits, and then this is plus b into L to the power 4 by 4 is 0. So this is another equation containing A1, A2 and A3. Okay, so this is say equation 2. And in a similar manner, I can write the weak form in terms of the third weight function, and then I will get using w3 x, then the w3 dx and w3l in the weak form. I will get P into W3 into 3 at L is L cube, so P L cube minus AE into integration of 0 to L. This term will remain same, A1 plus twice A2x plus thrice A3x square into dw3 dx. dw3 dx is thrice x square, so multiplied by thrice x square dx plus b into integration of these limits I should put, I'm sorry, 0 to L px into w3. w3 is x cube, so x into x cube, so I am writing x to the power 4 dx. This is also 0, and by doing the integration and putting the limits, I can finally get PL cube minus AE into A1 L cube plus 3 by 2 A2 L to the power 4 plus 9 by 5 A3 L to the power 5 plus B L to the power 5 by 5 is 0. So this is my third equation. Now solving these three equations, this 1, 2 and third equation, I can find out the values of A1, A2 and A3. Okay, so for that you can use any method, but I think because this is PL square, I can multiply the equation 1 by L and then subtract that from equation 2, and similarly what I can do is I can multiply equation 2 by another L, and that multiplication I can subtract from equation 3, and thereby I can eliminate one of the terms and two terms will remain, and two equations will remain, and solving them what we can get is we can get the values of A1, A2 and A3. Okay, and for simplicity I am not writing all the steps here, and I am just writing the results. Okay, so I will get, by solving, let me write just summary by you can solve these equations yourself by solving equations 1, 2 and 3 we get, what do we get? We get A3 as minus B by 6AE, and we get A2 to be 0, A2 to be 0, and then finally we get A1 as twice P plus BL square by twice AE. Okay, so these results we can find out by solving these equations 1, 2 and 3. All right. So let us box these results, and then if I use these values in my equation, approximate equation, in that case what I get hence U tilde will be A1x, so A1x plus A2x square, since A2 is 0 it will not be there, then A3x cube, and thereby if I put the value of A1 I get twice P plus BL square by twice AE into x plus A3, so minus B by 6AE into x cube, and then if we simplify it we will arrive at the original equation. So we can get 12 AE here, and then I will take x common, then I will get 12 P plus this is 6, no? So 6 BL square minus twice B x square, and this was exactly same as our original analytical solution. Okay, analytical solution, because if you see all these terms are divisible by 2, so I can cancel, I can take 2 common, and therefore in that case I will get the expressions that we got from the analytical solution. So I will get 6p plus bl square minus b x square into x by 6AE. Okay, and this is exactly same as the original analytical solution we have got earlier. Okay, so since we have already got the true analytical solution from that cubic approximate solution. So there is no point in further increasing the order of the approximate solution polynomial. All right. So with this cubic solution, now let us see whether the natural boundary condition at x equal to L is satisfied or not. Okay. So we have now u is this, u as a function of x is this, and this I further simplify as ux equal to six p plus bl square by 6ae into x minus bx cube by 6ae. Okay. And therefore, what is my du dx? Du dx is 6p plus bl square by 6ae minus twice x square, so b x square by twice ae, and hence my du dx at x equal to L is what? Is 6p by 6ae plus bl square by 6ae minus bl square by twice ae. Okay. I think some mistake I have committed, maybe. Let us see. 6p a1 is twice p plus bl square by twice ae, fine, and a3 is minus b, just a minute, minus b by 6ae. So yes, then if it is 12ae, I think somewhere I have committed mistake here. 12ae, so 6 into 2 is 12, 6bl square into x, and here it is twice bx square, fine, twice bx square, which is equal to 6p plus 6p plus This is where I have done the mistake. You see, I have divided by 2, so there should be a 3 here. This is where the mistake is there. There should be a 3 here, and therefore this is 3bl square. Let me write it again. So 6p plus 3bl square, and therefore I should have a term 3 here. This should be 3bl square, 3bl square. So I have 3 here, and this here, so this is half, so I get finally p by ae plus bl square by 2 minus bl square by 2, and this is my p by ae. And therefore NBC will be what? NBC will be AE du dx at x equal to L. So when I multiply it by AE, then I will have AE du dx at x equal to L, and this is nothing but P. So this solution is giving me, it is fulfilling the natural boundary condition at x equal to L. So this is a true solution. Okay. So if you are interested, I can give you a table which shows what are the boundary conditions for cubic, linear and quadratic solutions in a tabular form. Let me write the table for you. So this is my solution type, then the value of u or u tilde rather, and then du dx, let me extend this, then du dx at x equal to L, and AE du dx at x equal to L. So first solution u tilde del u tilde del x del u tilde del x at x equal to L, and this is my AE times del u tilde del x at x equal to L. Okay. So first my quadratic linear solution. First linear solution, then we'll write quadratic, and then we'll write the cubic solution. All right. So linear my u at x final solution is thrice p plus bl square by thrice ae into x. So del u del x is obviously thrice p plus bl square by thrice ae, and del u del x, since it doesn't depend on x, therefore it's a constant, so this will be same value, so thrice p plus bl square by thrice ae, and when I multiply it by ae I get thrice p plus bl square (3) or p plus bl square by 3. So natural boundary condition is not fulfilled. I can add probably one more column for remark. NBC fulfilled. Here it is no. And if we take quadratic solution, quadratic, I didn't solve it here, but I am giving you the results. It is 12p plus 7bl square by 12 ae into x minus bl by 4 ae into x square. So this is the solution, and del u del x will be obviously 12p plus 7bl square by 12 ae minus bl by 4 ae. Sorry, it will be twice x, so it will be this will be 2. This into x. Okay, and at x equal to L, this will be finally 12p. If I simplify, then I will get 12p plus bl square 12 ae, and ae times this value will be p plus bl square by 12, bl square by 12. Again it is not fulfilled. and cubic case we have already seen. The solution was twice p plus bl square by twice ae into x minus bx cube by 6ae. And partial derivative is 12 twice p twice p plus bl square by twice ae minus bx square by twice ae, twice ae, and this value is p by ae, and hence ae times this value is just p, so this fulfills the NBC. Okay, so this completes the table. You can try to find out the solution for quadratic case, and you can verify your results from this. All right, so this is the way we can use classical Galerkin's method to solve this axial deformation problem. All right. We have seen how the linear, quadratic, and cubic polynomial solution performs for the axial deformation of axially loaded bar. And one more point to be noted in this method is that if we assume a polynomial solution as the approximate solution or the admissible assumed solution, then in order to converge that assumed admissible solution to the correct solution, to the true solution, it must be a complete polynomial. Okay, that means it must contain the terms of every order up to the order n if I am using an nth order polynomial. All right, now let us try to understand what are the disadvantages or difficulties of applying classical Galerkin's method or Rayleigh-Ridge method in the classical form. Whatever we have learned about the Galerkin method till now is called classical Galerkin's method because we are not using any finite element, we are applying the weak form over the whole domain. Okay, so in this classical method, the most difficult thing to start the solution is to find the admissible solutions for a problem. If it is a simple geometry and one-dimensional problem, then it is relatively easy to find the admissible solution. But finding admissible solution for a 2D or 3D problem is extremely difficult, if not impossible. In most of the cases, it is almost impossible to find a good admissible solution. For example, let us consider the case of this rectangular plate. Say it's a plate, it's a 2D body. It is fixed at the left end and it is loaded by a point load at the end, at the top corner, and say its length is L and its width is B. Now you know that if I take this as my x direction and this as my y direction, okay, as per this definition, then I know that my u is a function of x and y, is not it? So I must be able to find out some admissible solution u tilde which will be functions of x and y. Okay. Now suppose I consider a, say, quadratic polynomial. Suppose my u tilde xy is say a naught plus say a1x plus a2y plus a3x square plus say a4xy plus a5 y square. Okay, so this is a complete quadratic polynomial in x and y. Now in order to apply the essential boundary conditions, I know that u at 0 for all y when x is 0 must be 0. Okay, therefore if I put x equal to 0 in the assumed solution, then what I get? I get u tilde at 0 y is what? A naught plus a2y plus a5y square. Now this is the only equation I have to apply the essential boundary condition, where I have three unknowns, a0, a2 and a5. Now how can I find these values to apply the essential boundary condition? There is no obvious way, right? One thing I can do is that I can assume, say, y is also 0. Okay, say I can assume that I'll have y will also be 0. In that case, this term a2 will be 0, a5 will be 0, a4 will be 0, right? And a0 will also be 0. In that case, what will remain? If x and y both are 0 for x equal to 0, then I will get, in that case, I will get a0 will be 0, then a2 will be 0, and a5 will also be 0 by putting that condition. When x is 0, this will have to be 0. In that case, what I will have? I will have u tilde xy will be a1x plus a3 x square plus a4xy. Now my solution is dependent on y only through one term, so that obviously will not be giving me a good solution. Okay, so in a similar manner, the situation may be more complicated if I suppose instead of this rectangular plate, suppose this corner is inclined now. Suppose this support is inclined. Let me draw another figure. So this is, say, my inclined plate, the rectangular plate supported at an inclined support, and this end is fixed. Now here you see earlier at x equal to 0, my deformation was 0. Now, deformation is 0 at different values of x and y. Okay? And this problem is further more difficult to find an admissible solution. Okay? So it is almost impossible. Nearly impossible to find an admissible solution. And that is why it's very difficult, if not impossible, to apply the classical Galerkin's method for slightly more complicated geometry. This is a relatively quite simple problem. It's just a cantilever plate, but even for that, it is extremely difficult to find out the admissible solution. And that's why people have moved to the finite element method, so that we can handle complicated geometry and complicated boundary conditions. And now we will, in the next class, we will see how we can cast this classical Galerkin's method to the finite element counterpart, so that we can derive the finite elements on the basis of Galerkin's weighted residual method. With this, we come to the end of this class. I hope everything was clear. So you please practice at least the linear solution of classical Galerkin's method, and also try to find out the quadratic solution. And next class we will see how we can modify this method to find out the finite elements. Thank you.